All right, now I want to take a look at how the second derivative affects the graph and what it tells us about the graph. So, the second derivative is telling you how the first derivative is changing, right? So, if you had something like this here, let's say my tangent line looks like that. So I'm starting right now here with y prime positive. Now, if the second derivative is also positive, then it tells me, well, the first derivative positive means if I move over, the function's going up. Well, the second derivative positive is telling me that as I move over, the derivative is going up. The slope is getting steeper, right? And as I move over again, I still should be getting steeper. So starting with a positive derivative and a positive second derivative, I seem to be bending upwards here, right? Likewise, let's take a look at, so that was that. Let's keep the second derivative positive, but let's start off with a negative slope. So let's say that y prime is less than 0. So I'm starting off headed downhill, but I want y double prime to be positive. So this tells me that the slope is getting bigger. Well, if you're at negative slope of -3, let's say, and then maybe it gets bigger to a slope of -2. So first derivative positive means as I move to the right, I'm going downhill. But the second derivative positive means the first derivative is getting bigger. It's getting closer to a positive number. So it's going that way and then this way, right? That this is bending now. Let's grab a different color here. It looks like my curve is bending like that. I'm going downhill. First derivative is negative, but I'm going downhill less steeply because the second derivative is making my slope get bigger. Head towards 0 and then positive numbers. Here, I started off positive and my slope kept getting even more positive and that bent me upwards. It looks like actually in both cases I'm bending upward. This is what's called concave up. This is concave up, right? In both cases it's bending upward. If I was driving my car along this road, traveling from left to right, I would have my wheel turned to the left, right? I'm bending to the left. Likewise here, moving from left to right, I am bending left. So my driving in this direction here, going that way, I've got my steering wheel turned to the left, right? If this is my steering wheel, right? It's not, this is my steering wheel if I hadn't turned it at all, but my steering wheel now is actually turned to the left. I'm turned this way, right? This is what I'm doing along this curve or that curve. Second derivative positive is concave up, bending upwards. Next, what if I have a second derivative negative? Okay. And maybe you can guess that's going to be what's called concave down. And sure enough, if I start with a positive slope here, so I start with y prime is bigger than 0, but y double prime is negative, means my slope is getting less. First derivative positive means as you move to the left, your y value gets bigger. Second derivative negative means as you move to the left, y prime gets smaller. So maybe I was really steep here and not so steep there, and then not so steep there, and even less steep there. And so the curve, the graph here is bending downwards. I'm turning to the right as I move from left to right. I got my steering wheel turned in the other direction now, right? I'm bending that way. This is what's called concave down, right? It's bending downward. Some people might call it convex up. I'd understand you, but we just don't ever use that terminology. It's concave down. And then my last example here is, what if I start off with a negative slope and I have the second derivative also negative? So starting off with a negative slope and then getting even more negative and more negative and more negative, then indeed we see the same sort of downward bend. Again, if you're driving your car from left to right, the steering wheel is turned to the right, in order to make that corner. This is called concave down. concave down. So the first derivative, it tells us about whether you're going uphill or downhill. The second derivative tells us whether you're bending upward or bending downward. Okay. Now, let's go back to the example we did in the previous video. Here's the function that I had. I saw, without doing any calculus, that it had an intercept at 0 and it was positive to the right and it was negative to the left. I saw using the derivative that the derivative was 0 at 3 and negative 3. It was increasing in between them, decreasing on the opposite sides. Anyway, I had this graph here. Now I want to look at the second derivative. Notice there's a couple of things I can see. I can see bending here upwards. I can see bending here downward. There must be a spot in between where we switch. Well, that spot in between where we switch is what's called an inflection point. Inflection point, P-O-I-N-T, where the second derivative is equal to 0, or actually the second derivative is undefined. We'll get to that, but the thing is, when you switch from positive to when you switch from concave up to concave down, you've got what's called an inflection point. I can clearly see that somewhere in here, in fact, I can probably argue that it's right in the middle right there, that there's going to be an inflection point. The thing is, I see a couple other inflection points too, because I see here bending downward slightly. Again, I'm thinking about driving my car. If I'm driving my car along this road, I'm steering just a little bit to the right, bending a little bit to the right. There's a spot right in here where all of a sudden I start bending to the left, right? My steering wheel straightens out momentarily there. That straightening out of the steering wheel is what's called an inflection point, and now I'm bending to the left. Coming through here, straightens out momentarily, and now I'm bending to the right. Bending to the right, bending to the right. Oops, all of a sudden I'm about right there. I'm switched to bending upward here. So I can see right here concave down. I can see concave up, I can see concave down, and I can see concave up. Now, I haven't done the calculus yet to figure out exactly where these bends change, where the concavity changes, but I got a pretty good idea. I'm expecting 3 inflection points here because I can see 3 transitions from bending one way to bending the other way. Okay, so let's actually do that calculus now and see what we end up with. So y double prime equals, I'm looking at this thing now, doing a big old quotient rule. So I've got x squared plus 9 to the 4th power, x squared plus 9 squared. Again, let's just throw the 12 out in front just to make our lives a little easier. 12 times all this stuff. So that was the bottom times the derivative of the top. So I need a negative 2x minus the top times the derivative of the bottom, and the derivative of the bottom is 2 times x squared plus 9 to the 1st power times the derivative of the inside, which is 2x. All right, so that's a big derivative, but let's see if it cancels out at all. I'm going to factor things here rather than multiply out because I know what I'm going to try to do. I'm looking for inflection points. I'm going to look for places where the second derivative is 0, and so factoring is really the way I want to go. So I've got a 12. I see a factor of x squared plus 9 in both things there, and I see a factor of actually negative 2x. So let's factor out that negative 2x. So the negative 2x got factored out, that got factored out. So there's an x squared plus 9 left from here. The negative goes, the 2x goes, that goes. It looks like I still have a 2 times 9 minus x squared from this, because that got factored out, that got factored out. Yes. Okay. And that's all still over x squared plus 9 to the 4th power. Right. Now that this is factored in the numerator, this will cancel with one of those, leaving a 3. You got to be careful not to cancel in there because I haven't factored it yet. There's a minus sign, but now this is factored. So, so I've got y double prime equals negative 24x times Negative 24x times, let's get some like terms here. I've got an x squared and a minus 2x squared. That's going to be a minus x squared. And I've got a 9 plus 18, which is 27, all over x squared plus 9 cubed. All right, I think I'm seeing exactly what I want to see because I have inflection points now. Inflection points are essentially critical points of the second derivative. Right? Your maxes and mins were critical points of the first derivative. Your x-intercepts are critical points of the function. Anyway, inflection point here happens when this is equal to 0. Y double prime equals 0. Well, it's going to equal 0 when the numerator is equal to 0. So that's when x equals 0, or 27 minus x squared equals 0. So x equals 0, I had guessed that one. I had guessed that inflection point, right? There seemed to be some symmetry perhaps about the origin. So yeah, we got that one. And then I've got x squared equals 27. So x is, what's this, plus or minus 3 times the square root of 3. So again, this is where calculus textbooks drive me nuts because it's like they think you don't know what the graph looks like yet. So they say, oh, here's what you got to do. You say, okay, here's x equals 0, here's x equals 3 radical 3, and here's negative 3 radical 3, and you're looking at the second derivative. This is where the second derivative is 0. And then I got to check in between, is it positive, negative, or, what's it doing? Well, I got to look at the second derivative here and say, if I'm bigger than 3 radical 3, then this is going to be bigger than 27, and so that's going to be negative, and that's positive, and that's, negative, so I got negative times negative is positive, so the numerator is positive, the denominator is positive, and so this is positive, so this is concave up over here. Right? And then you say, okay, now drop below 3 radical 3, and suddenly the x squared becomes less than 27. So this is a positive number. This is positive. This is negative. So the numerator is negative and the denominator is positive. So all of a sudden you're negative second derivative. So you're going concave down through that stretch. Right. Then when you get to the other side of 0, then this changes from positive to negative. This was already, so this was positive, negative, negative. So suddenly you're positive again. Concave up. And lastly, when you get on this side of the negative 3 radical 3, then this x squared gets big again, and 27 minus that thing is going to be negative. This is negative, that's negative. There's 3 negatives on the top. This bottom is, well, the bottom is positive. The x squared plus 9 is positive. And so you got negative, negative, negative. 3 negatives multiplied together, there's negative, and so you're concave down. Right? Concave down. And so it's concave down, concave up, concave down, concave up. I knew that already. I knew what the graph looked like. It had to be this way, right? But the second derivative verified that yes, indeed it is concave up and down where we thought it was. But it gave us some very clear points of inflection. Where did it change from concave up and concave down? So I can graph these points more carefully and get exactly where, get a better idea of what this graph really looks like. Okay. So there you go. The second derivative is telling us about inflection. How is the curve bending? When the second derivative is equal to 0, we have what's called an inflection point. We change from bending downward to bending upwards or vice versa. There you go, the second derivative.